Hey Algebra 2, let's continue on with our lessons. First we're going to do a little bit of review, and then we're going to get into imaginary numbers and what they really mean, how we graph them, how we deal with them, how we do math with them. So let's review first. First of all, solve each equation for x. Okay, yes, we are doing this. If we solve this first one for x, we get x equals 1. Okay, next one, x equals -1. And just look at what we're starting with here, right? On the next page, which I'm going to skip past, we have x squared minus 1 equals 0. If we solve that one, we get x squared equals 1, square root of both sides, x equals 1 and -1. We get two answers. That was C. And then D, x squared plus 1 equals 0. We actually have no real solution in that one. Okay, all right. So before we really begin with the work that you see in front of you, I want to explain a few things. First of all, make some room in your classwork just to do a few graphs. Okay, first I'm going to do just a basic number line. Okay, very basic. You guys started doing these when you were in grade school. So if we remember, if we take any number and we multiply it, I don't know what I wrote there. Sorry, it happens every once in a while. Multiply it by -1, it rotates the number on the number line by 180 degrees. Okay, so 2 times -1 equals -2. And then -2 multiplied by -1 gives us +2. So we have a 180 degree rotation on a number line. All right. Is there a number that we can multiply that corresponds to a 90 degree rotation? So what if we wanted to do a 90 degree rotation? What type of number would we come up with? It is a strange question. I don't know why we would want to come up with a number that corresponds to a 90 degree rotation, because we're just doing a number line, right? We weren't doing a coordinate plane graph where we had 4 quadrants and x and y and positives and negatives. We're just messing with a number line. Sorry, I'm trying to fill your audio space while I draw another number line. So if we wanted to take this 2 and map it, you know, we've got a 90 degree angle here. We're mapping here the 1, the 2, the 3, the 4, like what does it map to? This would be a rotation of 90 degrees. What's the point? Why are we doing this? You may hear some jackhammering in the background. I'm trying to get away from it, but it's sort of difficult to do, so I apologize. I just want to remind ourselves that this is the real number line that I'm working with. Okay, these are all real numbers. So now our screen looks like the coordinate plane, but what are those vertical axis, hash marks for? Like, how would we even label those? Well, and I've always laughed when I teach this lesson, but since we imagined such a number could exist, let's call it the imaginary axis. The imaginary axis. So we're going to divide this imaginary axis into units, and the units are called I. Oops. And the I stands for imaginary numbers. and I know it's sort of humorous. I always thought that mathematicians sort of ran out of things to do, so they made up numbers and called them imaginary numbers. And that's not true, but it's just something I always thought of in my mind because it's just so funny. Like, okay, that concept doesn't work, so we need to make up an imaginary number to make it work. But this is what we're doing. When I want to rotate something 90 degrees, it rotates into the imaginary axis line. So if we go to the point 1, if I rotated it 90 degrees, it rotates into the imaginary axis I. So 1, 90 degrees rotates to I. 2 rotates to 2I. And if we go to the negative real number line, negative 2 would rotate to negative 2I. Negative 3 would rotate to negative 3I, etc. So that's what we're doing here is negative 2 times I. Okay, negative 3 times I. All right, what happens if I take my vertical numbers and I multiply those by I? So here, if I have negative I, if I multiply negative I times I actually get 1. Okay, negative 2I times I get 2. Okay, if I take 3I and I multiply it by I get negative 3, etc. Okay, so that's when I'm rotating the point 90 degrees counterclockwise. Now, if I perform 2 90-degree rotations, it's the same as performing 1 180-degree rotation, right? And you guys are saying, yeah, we know that, we're good. So if I take a number and I multiply it by I twice, I would be on the negative side of the real number line. If I take a number and I multiply it by I twice, I end up on the positive side, right? So since 2 rotations by 90 degrees is the same as a single rotation by 180 degrees, 2 rotations by 90 is equivalent to multiplying by I twice. Therefore, we are learning that I squared is equal to negative 1. Okay, that would be a very important thing to remember, correct? Now, why is this useful? If we remember in the opening exercise, we couldn't solve this equation. And we'll show you why. If I take the square root of both sides, okay, the square root of negative 1 is not a real number. Okay, I'm stuck, right? So x equals, actually it's plus or minus the square root of negative 1. But now that we know that I squared equals negative 1, therefore I, if I take the square root of both sides, equals the square root of negative 1. Okay, this is an important thing also that we're going to continue to use. It seems a little weird, but this new imaginary number, I, already appears to solve problems that we could not solve before. Okay, this helps us out immensely in algebra. Gosh, if you remember, we would use the quadratic formula for solving equations that we just couldn't solve easily on our own. Over 2a. When we get negative numbers underneath this radical sign, we are always stuck. Well, now we're not so stuck anymore. We have an I that we can use to help ourselves out. All right, let's move on. Oh, we already did this. I needed to explain one more thing to you. I almost forgot. Okay, this is called a complex number. Okay, we have A and B are real. Just like we can represent real numbers on a number line, I can actually represent complex numbers in a different coordinate plane. So if I look at, we're just going to say A plus BI. So if I go over A, okay, here, oops, is going to be the distance A, and here will be the distance BI, with this dot representing A plus BI. So we're going to be graphing these pretty soon. So we have complex numbers which have real parts and imaginary parts, and we can add, subtract, and multiply these complex numbers. So let's start by adding. I'm going to do this one pretty slow and with a lot of detail that you may or may not need. So when we add these things, we're actually going to collect like terms. So if we said that I had A plus BI plus C plus DI, where A, B, C, and D are all real numbers, I can actually break that up into A plus C plus, B plus D I. So let's try that here. That gives me 3 plus 7 plus 4 minus 20 I. So 3 plus 7 is 10, 4 minus 20 is negative 16 I. And there's our final answer. Now obviously you don't have to break each problem into that much detail. Most of us could get from here to there without writing that middle step, and that's totally fine. Let's try another one. So here we have subtraction. Subtraction poses just a little bit of confusion. When I have a negative sign in there, remember to remove the parentheses. I need to distribute that negative. So I can say that 3 plus 4i minus 7 plus 20i is what I'm doing. Now let's start collecting some like terms. 3 minus 7 plus 4 plus 20i. 3 minus 7 is negative 4. 4 plus 20i. And we have our final answer. Okay, multiplication with complex numbers. I can break this into, let's see, if we had A plus BI times C plus DI, we're really foiling it, okay? We do first outer, inner, let's see, BCI, and then last BDI squared. And remember that I squared is negative 1. So let's go ahead and FOIL this. I get 1 first outer minus 2i inner plus 2i and last minus 4i squared. Those cancel. I have 1 minus 4, and remember I squared is negative 1, so 1 plus 4 is in fact 5. Right. So with this last example, let's verify that negative 1 plus 2i and negative 1 minus 2i are solutions to this right here. All right. We're just going to plug them in. Negative 1 plus 2i squared, negative 1 plus 2i plus 5 equals 0. If I square that first one, 1 minus 4i plus 4i squared minus 2 plus 4i plus 5. Collect like terms. 4i squared minus 4i plus 4i, those cancel, plus 1 minus 2 plus 5. Okay, cancel those. This becomes negative 4 plus 1 minus 2 plus 5 is in fact 0. Okay, try negative 1 minus 2i. I have negative 1 minus 2i squared plus 2 times negative 1 minus 2i plus 5. Go ahead and FOIL that. And distribute. Rearrange a little bit. I'm replacing that I squared with a negative 1. Okay, plus 4i minus 4i, plus 1 minus 2 plus 5. So those cancel. I have negative 4 plus 1 minus 2 plus 5 does in fact equal 0. Okay, both solutions. Awesome. And our lesson summary. Okay, why we need I, right? And then how we work with it. But a few practice problems and you guys will be awesome. Good job today.